Okay, good morning, everybody. I noticed that um the recorded lectures was watched by quite a few students. So it's good if you guys need it. I can always go back to watch the video as needed. So we are going to finish diodes this week. So today and Thursday. Just a reminder that you have your we have our middle term. Our first middle term on Tuesday next week. It's same time, class time. Make sure you come here early so that we're ready. So we're gonna make sure you get your IDs. Okay, we're gonna check your IDs because this is a very cramped classroom. And also when the class starts and then the midterm will be available, there's gonna be a access code that you have to input the code before you can take the 5 problems. So as I explained in the beginning of the class, when you get started, make sure you do all 5 problems. Of course, we're going to drop one from 5, so which means the worst one that you do, it's going to be dropped. But you design your best approach to handle it. Some student might say, okay, you drop it one anyway, so I'm going to just do 4, do my best. I might not have time to do the 5th one. That's fine, up to you. Or some students might say, okay, I'll just try all 5 and just give my luck and see which one I'm going to do the best. Is it going to be counted? Yeah, right.
I might be this with Nasa is so worse. Everybody drops their lowest for
Yeah.
It's not the question that lowest as a class.
No, everybody dropped their lowest grade in that exam.
Oh.
So you could drop 4, you could drop 2, another one could drop 3. I mean, if you got 100% on every problem, still drop 1. Yeah. And then the homework solutions are posted ahead of the due date. I know that this is a little awkward because say, okay, well, the purpose of homework is to have you guys exercise and then learn the contents. It's not really to punish you for not being able to know how to do the problem. So I told my TS, saying, well, if a student copying from the solution, I'm hoping that you still learn something during the process of copying that solution. So that's my goal. So, okay, I'm not here to really try to make your life difficult, because if I post the solution too late, you guys say, okay, well, the solution was not even posted and it was on the exam, right? So I did it wrong in my homework. So how do I? So I thought, okay, let's post it ahead of time. But my suggestion is still going to be do it yourself instead of copying the solution, because when you copy, you might not knowing what you're doing, but when you do it, and you can refer it to the solution. So that is going to help you to understand the contents, right? So make sure, you submit your homework on time. And I just extended project number 1 about another week, so you guys will have more time to do the project. And make sure you submit your project on time. And I already have some students come in to say, oh, I forgot to submit. And other students say, well, I couldn't get my computer to work. I couldn't submit. Whatever, this is always a reason. But if you happen to be sick, or you have to be some reason that you could not overcome, we certainly will take into that account, but you'd have to have evidence. Like say, one student got a car crash and had a police report. Okay, we'll take it. That you happen to be in the hospital with your mom and somebody, okay, have a doctor notes, we'll take it, okay. But otherwise, we wouldn't take it. But also, 1 or 2 students ask, can you submit the solution, the homework and projects in a different format, like other than PDF? Unfortunately, no, because as I just saw the student email me, and the file was 29 megabytes, which is apparently way too big. And also, when you submit a like GIF or some format, sometimes it could be very difficult to read in some devices. Like my computer even not open PNG file. I have to select some sort of search for something to open it anyway. So there are many tools available. I believe the university has tools that you can download. And also there are many free tools online that you can use to convert your any files into a PDF. One PDF file, we only accept one PDF files. Yeah, any questions? So our second exam is on November 6th and on December, which day I don't remember, but one of the days we have external speaker coming from ASMO. That's the best company that you could work for. They have a lot of our students, so they want to talk to you guys and have you guys give you guys a real world examples what they do at work and answer your questions, any question you might have. And the final exam is December 18th. Any other question? Just recap on still days. Yeah. Okay. So we're going to continue. So last week we talked about small signal models of diodes, and we had we talked about how to solve a diode small signal circuit. And one of the question was like if you have a voltage source, you have a current, you have diode. Let's say you have a resistance here. And what happens if the voltage has a small, like overlapping voltage, a small signal or something, or change? In that case, what we said was we can do superposition by using solving the DC. Like here, we can use the ideal model, 0.7 volts drop, plus another circuit which has a small signal. And this is the small signal that's got a little wheel. And this is the RD. And the RD was solved from the figure you can see. So some students said, well, where did that 0.7 volts DC voltage go, right? We know that you can use superposition by separating these two terms. We can solve this one first, we can solve the other one second, right? But remember, this diode is equivalent to now is going to be 0.7 volts that drop plus a little resistance. So ideally, like if you might look something like you might have an actual circuit. Why didn't change the color? Okay, it doesn't change the color anymore. So you like this. Oops. So this is your 0.7 volts drop, and this is your VD, and this is your little VD, and this is your R, and this is your RD. So you can always do superposition based on 1 voltage or 2 voltage, but see, this can be equivalent to a voltage source. So you can eliminate that voltage source, right? Then you can do the small signal only. So this is very simple for a signal to for a diode to be decomposed into a small signal. So this is where you have the equivalent circuit. Now you can solve for what's so-called an incremental current. Okay, let me explain to you what it means. But anyway, let's start with this. So you have the input voltage, the small signal imposed on that DC voltage, right? Remember the original circuit is like this. This is the original circuit, right? So now what we're doing is we got rid of the DC, we got rid of the 0.7 volts. We have this whole small signal circuit, which is again superposition over the overall circuit. So we get, now you can easily calculate the current. And you can see here is only the small signal voltage divided by the resistance plus RD. And one of the students asked me, okay, why can't we just do the small signal like this? He said, if I do superposition, can I do the voltage without like the resistance? Well, this is wrong. The reason because when we do superposition, we do like voltages and currents. The actual components like inductors, resistance, and capacitance, you don't do superposition on those. Okay, they stay. Only you superpose the source, the sources. Yeah, go ahead.
As long as we make that RD plus R big R.
Well, that's okay.
That would
Yeah, that's probably something I wouldn't even get there because it's too complicated. So so your question is now we got the incremental current, and then what does it mean? Well, what it means that remember you also when you do superposition you also have this circuit. That's your VDD and your R and your 0.7 volts. So you really have your original ID equal to the VDD minus 0.7 divided by R. Now we don't have the RD here. One of the reasons is the RD is relatively small, so we basically don't even consider it. But the other thing is that this little RD is due to the variation for the input. It's not by itself there. If you don't have the small signal, that little RD actually is gone. It's like the change, the derivative of that change gives you this little RD. Right? So that's important to understand. So now your total current is going to be let's call it IO equal to ID plus third ID. And that third ID is called incremental current. And so it's called incremental current. So if we draw the waveforms, and you're going to see something like this. So this is your ID. And then this is your third ID. So you have two currents. One is the DC current caused by the DC voltage. Another one is the incremental current caused by the small signal superposed on that voltage source. If you add these two, you'll get a final waveform like this. So that's your final current waveform. The two dotted lines are actually mathematically, we found them and we superpose them together to get the actual final current. Yeah, go ahead.
Again, quickly, why the diode breaks down to the 0.7 and the RD when you like separate them like that?
Yeah, so the diode, remember the diode has when you apply DC there, it performs like a 0.7 volts DC when your current is large enough. So let me go back one slide, you can see better. So on this slide, so this is your on this side, when your current is big enough, your voltage is constant 0.7 volts. That's like when you apply DC. But when you have a DC, when you have an AC, a small signal on top of AC, that AC actually changes. When that change, it's no longer a fixed point. So that change introduced this diode to perform like a little resistance for that AC signal only.
So the small signal is AC voltage?
The small signal is the AC voltage, yeah. Okay.
So in AC, diode at a resistor?
In AC,
In small signal AC?
small signal AC diode performs like a resistor. Yeah. How do I change color?
Okay. So then when you have a large signal, the voltage is consistent, 0.7 volts?
Yeah, well, remember there are three possibilities. There's an ideal model,
Yeah.
there's a 0.7 volts constant voltage model, and there is a spice model. So that spice model will determine, well, and also it's going to decide where the operating point is, right? So remember this curve is like this. So if you're operating like on here, that's 0.7 volts, right? But if you're operating below that, it should use a spice model, right? So this final decision is based on where and how you operate the diode.
So you check what's the voltage at my diode, and then what do I use to represent it?
Right.
Okay.
And of course, for you guys, for this class in particular, for the exams, we don't ask you to determine. We actually tells you, we already tell you, okay, well, it operates here, and use this model, right? Okay. So
Give us the small RD as well.
it gives you what?
This RD.
Well, that RD, yeah, well, it depends. It might actually ask you to find RD. You know,
Given the current ties, given the.
well, you can find it because you can take the, you know, if it gives you what the slope is, right? You can find the RD based on that slope. The slope is 1 over RD. And of course, you have to find the operating point. Like if it operates over here, the slope is bigger. But if it over here, you see, your RD is going to be bigger. But if it's like operates at vertical points, there's no RD because it's going to be 0 because that ratio is like infinity, right? Okay, so now we're gonna go ahead to look at a couple examples. We plus, okay. So let's see. So the problem is, okay. So we have this circuit. Basically, this original circuit gives you the indications, voltage power supply, through resistor, through a diode. And here, it just mark up all the components, all the variables that we need to solve. So you have 10 volts applied at the top. You have a resistance, you have RD and VD marked on this diagram. So initially, we want you to find out what is the current if this operating at a DC mode. So at DC mode, apparently, we can say that so in DC mode, we will say that ID equal to 10 volts minus 0.7 divided by R. So that gives you your current. Why can't I change the color? I don't like the black color because it blends with the existing. Microsoft use the ink twist. Oh, this won't even go away anymore. Okay, that's okay. Okay, so initially you can find the RD, the the current. Sometimes they call this a quotient current, which means operating point. So that's where the DC flows in. And then secondly, at this point, you can start to apply like a small signal on top of that 10 volts. And then therefore, you can see that this circuit was redrew to show how the small signal is connected. So basically, let me actually do this. So basically, this would look like this. So if you still doubt, what happened to that? It basically looks like you have a DC and an AC signal applied on the left hand, and then you have resistance, right? You have VD. Now, once we find the DC current or the quotient current, we can draw the small signal circuit, which now remember we can eliminate that DC voltage. We can eliminate the 0.7 volts, right? So we got this circuit. So from this circuit, we can find out the little current. This current.
VS, the small.
If VS is the small signal, divided by R plus RD. So the question is that how do you find RD? In the example, if you go back 2 slides earlier, remember here we need to find the slope of this voltage. And then if you guys remember, the voltage relationship was ID equal to IS e to the power of V over VT. So that's the current relationship. Now what you need to find out is the slope. So by some mathematical derivation, we can find out that RD is 1 over slope and equal to VT over ID. Then this ID is the DC current. Okay. So you asked earlier, how do I do that? Well, we tell you that you can find RD is VT over RD. ID is the current, the DC current that we just calculate from the other equation. The top left corner, we have that ID. Let me make this a little bit better. This doesn't look very good. Will be. So now I think, let me see. So in the 10 volts by 7 divided by 10K. So this is 10K. So we found this to be 0.93. Right? And VT is going to be 25 millivolts. So RD equal to VT is 25 times 10 to the minus 3 divided by ID 0.93. That's milliamps too. Millivolts divided by milliamps. That gives you, okay, let's forget about that minus 3. Just use 25 divided by 0.93. Screen is lagging. So 25 divided by 9.3, that gives you almost 0.93. 26 ohms. Okay. 26.9.
What was VT again?
VT is given.
Oh, it's given.
It's a 25 degrees C, it's 25 millivolts. It's easy to remember.
The equation for ID, where did we get that again?
The equation for
SE to the something.
that was given in the very beginning of diodes.
Yeah, that was the LT.
The SPICE model.
Yeah, SPICE. Oh, that's the curve from 0 to
7. Yeah.
7.
Right.
Okay.
Yes.
On the
divided by rad for 0.7, that's the constant. Why do you subtract 10 minus the constant?
No, for the DC operation, the diodes like a 0.7 volt constant voltage drop. Yeah, the voltage drop across the diode is 0.7. So you have to subtract that 0.7 to get the real current for the DC current.
So how would I look at this and be like, I'm gonna use the SPICE model? You know what I mean?
Well, because we have a small, it would,
You use a SPICE model when you have a small signal. You know, when we in the early examples, when we want you to find out what is the voltage, you know, it's all DC. You don't have to worry about RD because there's no RD, there's no small signal, right?
Yeah.
Okay.
But
Any
that
question
makes
there? All right. So that's the example, and so here, this example basically is going to be similar, but what it does is that it got 3 diodes altogether, and it got RL also connected. But what it says is that they said that there's plus and minus 1 volt on the DC power supply, and they want you to find out what is the fluctuation as this load side. Let's because it's VO. If you have a 10 volts constant, so apparently you subtract 2.1 volts, the 3 of them in series, so it's 2.1 volt, right? So 10 minus 2.1, 7.9 divided by 1K, that gives you the voltage or the current through that branch. But here, the trick is that we have a change in terms of that input voltage. Now, depending on that change, if that change is like fixed, like if one student, you know, if all the students, let's say, doing experiment in the laboratory, you know, some students get 10 volts, some students get 9 volts, some students get 11 volts, but it's a fixed value. So regardless what the value is, but it's fixed. Then you don't have to worry about the small signal model. You don't have to worry about the RD because it's fixed value, it's DC. So if those are fixed, you have let's go, and then you would have 3 possibilities, right? Then you have 10 minus 3 diodes. Remember, 3 diodes give you the total voltage of 2.1. 2.1 divided by 1K and gives you like 7.9 milliamps. Okay. Now, of course, if it goes to 11, it will simply just goes to 8.9, or you can go to 9, it will be 6.9 milliamps. So if you think that that voltage is fixed, now you're okay. But if that 1 volt is actually not just a fixed constant, actually it varies over time. That is where this small signal comes in, because it's no longer like a fixed value, but it actually changes. So your 10 plus 1 minus 1, it goes like this. And that peak to peak is plus 1 and minus 1. So in that case, we have to solve for this little RD. And that little RD is going to be given by VT over ID. And so now we're going to use that 7.9 because, and you might say, why do you use 7.9, not 8.9, not 6.9? Well, because the average in the middle is a 10. So you got plus 1 and a minus 1. So the +1 and -1 is actually like a transient value peak, top peak and bottom peak. The average value is 10. So we use that average to represent, to calculate the resistance. So now we can find out this is going to be 3.2 ohms. Okay. And this is one of them, but you got 3 RDs, it's going to be 9.6 ohm. So now you would have your small signal model comes to be yeah.
That's if we treated it. So if the plus minus is
Yeah.
not an oscillate, we can treat it as volts.
If it's 9 volts, yeah, yeah. I assume if they're all constant, like it goes to 11, constant, or it goes to 9, constant. But actually they're not constant, so right, that's why we are going down to so for the resistance. So this resistance is 9.6 ohms, and this is 1K. And you're gonna find this. Okay, so we're gonna find this third ID is gonna be third VD, which peak to peak is like 1 volt, 2 volts peak to peak, but so one side is 1 volt. So really it's 1K is 1000 plus 9.6. So it's 1 over 1000, 9.6. It's not a lot of change. It's actually
It's in a rounding error.
yeah. So we can also find what the third VO. So third VO is going to be that ID times RD, which is again here it's 9.6 ohms. So I'm not going to go to the math. So actually it gives you around 19 millivolts. So it's not a lot of change, but there is some change we can see. So the next part of the question about what happens if you connect like 1 kilo ohm resistance right in parallel with the diodes. So that will make it a little bit tricky because first of all, you see, can you say that R, the 1K on top and RL at the bottom, can you say that they're in series when you connect the point? Like,
RL is not in series with R. Oh, well, you just.
so can you say RL and R in series at all? You cannot say that because they're diodes, right? They're diodes. And apparently, if VD is DC 10 volts, so right away you see the voltage drop here is 2.1. And the voltage over the the top portion is 7.9. So this is a 2.1, and this is 2.1, and then that's a 7.9. So now we can determine the relationship of current. So the current over here, let's call it IL. I'm going to separate this to a different question. So IL is going to be 2.1 volt divided by 1K. It's give you 2.1 milliamps. And how much is I? Let's call it I over here. So that's I. Let's call it IR. So IR gives you is 10 minus 2.1 divided by 1K. Give you 7.9 milliamps. And this is ID. So how much is ID? So apparently this current flowing to ID, that's IR minus IL, so that's 5.8 milliamps. So you got a different current. So the reason I do this is because now that RD actually changes, right? The reason is this ID is going to be VT over ID. So instead of 9.6 milliamps, now it's going to be 25 divided by 5.8 milliamps. That gives you more like 4 point some ohms, almost like a almost 5 milliamps. Anyway, so we're not gonna do that anymore. So you guys see this RD changes. So now when you do the actual circuit, the equivalent circuit eventually will become also very different. So it becomes, I know some of you from back may not be able to see, but I don't have space. So the eventual circuit will look like this for the small signal. This is RL, this is R, and this is RD. And this is V. Yes, go ahead.
Yeah, 2.1 volts. Where'd that number come from?
3 diodes.
Oh, 7.7 times 3.
Yeah.
Okay.
So the final equivalent circuit is going to be this little resistance in parallel with this RL. So how much the equivalent current would you get? Well, now because it's 1K in parallel with something like 5 ohms, really it doesn't change very much, does it? How much would this give you?
Well, it's not really 5 ohms, it's like 4.3.
4.3, yeah.
And it goes like to.
Right, because the 5 ohms 1K, I mean, the resistance really just reduced a little bit, right? So overall, the equivalent circuit, whether you have this load or you don't have this load, I mean, this side of current didn't change very much. Okay, so this is I think we're probably going to be just so much on that resistance. I actually this is I was going to show it over here, but we did it on the previous slide. That's fine. So one of the, I think I mentioned about this diodes being operating in the breakdown region. I want to recap that. So all diodes, the whole spectrum of diode look like this. This is VD, this ID. The whole spectrum of that curve look like this. So far, we have talked on the first quadrant. First quadrant that is when VD increases, ID increase, at some point it reaches 0.7, and your small signal, all that stuff, good stuff are in the first quadrant. But for some diodes, if it's in the like the third quadrant, so what happens is that it's going to, now let me also draw this voltage. Okay. So this is positive half and negative half. So when the voltage is negative, when voltage like flip direct negative, initially there's no current because it's reverse, we call it reverse biased or like voltage blocking. But at some point, it will break down. The barrier is broken. When the barrier is broken, the current starts to flow. And that phenomenon is very similar to this one, but even more like dramatic. And that this current, this much of large current, as we explained before, if the diode keep working on this, it's going to increase current, and current multiplied by voltage is the losses, and then losses generate heat. So that device is going to become very hot, and it's going to burn, and eventually it's going to like smoke. Yeah. But for some diodes, it is designed to work in that region. That's called a Zener diode. A Zener diode works perfectly in the breakdown region. It can take such amount of current and heat, but of course, if it's too much heat, you have to have a heat sink to dissipate the heat. But what it does is it gives you a constant voltage. it gives you constant voltage. So regardless how much current flows in there, or cannot be too small though, because eventually the Zener diode works in this region. It works like in this region. It's not in here. Like this region here is not the region, like it just started to increase current. That region is not good because the current is not constant. I mean, the voltage is not constant. It's still a function of voltage. But once it reaches the breakdown point, the voltage becomes a constant. And we use that property. We use that property to design a voltage, like a constant voltage output. Like in this case, you have this circuit, which you have a voltage coming in. It's 10 volts plus minus 1 volt. And if you don't have this Zener, if you have only 0.5 and RL in series, what happens? So when the voltage source change, the voltage across RL is going to change. Same amount of percentage, right? Let's say if RL is also 0.5, you know how much would you get in terms of voltage? So if it's 10, that's 5. It's 11, that's 5.5. If it's 9, that's 4.5. So that voltage changes, right? So let's say instead of, you don't want that change, even though the voltage source change, but I want the voltage across RL is constant. You can simply put a Zener diode over here, and the Zener diode would stabilize the voltage regardless of that change. So in this case, we have a 6.8 volt Zener, which means if input is 10, I get 6.8. If input is 11, I got 6.8. If input is 9, I got 6.8. It doesn't matter. Your input can change. I don't care, but my output is constant. Yes, the current, of course, is going to change. Well, depending. The current over RL is not going to change because the voltage is constant. But the current over that R is going to change because you use 10 minus 6.8 divided by 0.5 gives 1 voltage. You use 9 divided 9 minus 6.8 gives you another voltage, current. Yeah. The voltage drop between the voltage source and Zener, it changes based on how much the input changes. Yeah. Yeah.
Wouldn't the voltage across the Zener as a whole slightly change because we have that RC?
You're absolutely correct. It does change a little bit because it depending on the slope. If you work on this like lower region here, it doesn't change very much. Probably less than
The slope is
practically infinite. Yeah. But if you work in that region, it's gonna. So when you guys go on DGK to find a Zener diode, it specifies at what current it will give you the constant output voltage. If your current is too small, it's not going to work. Okay, so in this case, we can have a couple, I guess, different combinations just to show how this works. Okay, let's say in this particular case, we can do the example saying that well, we have to know the resistance RL, to know the total current across this Zener diode. I think last week we already have a couple examples. Let's say the first example will be RL is equal to 0.5K. It's just simple one. So if RL is simple 5K, and then we have IL is going to be 6.8 divided by 0.5, that gives you 13.6 milliamps. And then we have I, let's call it this one. This is IZ, IL. Let's call it IS. So IS is going to be 10 minus 6.8 divided by 0.5. So it's going to be 3.2 Okay, so now I think I want you guys to look at it. Is this possible? Is this possible? So I got IL, which is the current across the resistance 13.6. But then I got xenon diode only supply how much? 6.4. Where would that current come from? The additional current come from? You might say, okay, well, the xenon diode can conduct current this direction. Maybe this current coming this way. Well, the problem is that you current coming this way, you don't have 6.8 volts. You got what? 0.7 volts, right? Because see, this is ground. You cannot have 6.8 volts across this way. So this design absolutely will not work because the current over RL is too big. Okay. So how much you think this current maximum can be? I mean, the maximum you cannot be more than 6.4 because if it's 6.4, there's no current over here. If there's no current here, you see which point it goes. And you guys, if no current, it goes to the origin. So it doesn't work. So this one, we say it's not going to work. So we have to increase RL. So we increase RL to, how much we're going to increase? Increase to 2K. So we're going to have IL is going to be 6.8 divided by 2K, 3.4 milliamps. Okay. And then IS now is going to be still 6.4. And IZ becomes IS minus IL. It becomes 3 milliamps. So most likely, this is going to be okay because it's 3 milliamps already. And apparently, you guys can also look at you can also look at how much losses. So the loss is going to be P xenon diode going to be IZ times like VZ is 3 times 6.8. So it's almost 21, 20.4 milliwatts. So the loss is 20.4 milliwatts. I mean, you might say it's not a lot. Yeah, that's true. It is not very big. But if you consider the xenon diode is so small for this kind of device, it actually is quite a bit of heat. Okay. Now, of course, you want more current, like an amp. Sometimes you have a circuit, you have amplifier, you have speaker that you go to amps. Apparently, that loss can increase dramatically.
That's just for the current that doesn't change.
The current does change when the load changes. And also, the example also particularly was looking at what happens with the voltage change and the RZ would also change. Okay, now RZ change will actually introduce like the output voltage will also change as well. So I think we probably can skip that for now because I do want to get into rectifiers. So a rectifier basically changes AC into DC. Just a little bit of history. Why AC? Why not DC? Because we use DC quite a bit, right? We charge our phones, laptops, a lot of DCs, yeah.
Because the AC is better for long range transfer.
Yeah, that's true. That's true. Yeah. Okay, over there.
On top of that, you can use the gauge used for the cabling is much smaller. Than
Yeah.
DC.
Right. Yeah. Yeah. Very good.
Generators. They
Yeah.
produce AC powered generators.
Well, generators can produce either AC or DC depending on what type of generators. Okay, you can have DC generators. You can also have AC generators. In fact, when electricity was initially invented, it was all DC. It was all DC. And also at some point, there was a debate between Tesla and Edison. Yeah. So Tesla was in favor of AC, I believe, and Edison was in favor of DC. So The problem is that if you say you have a generator at home, you want to generate and you want to use it, it doesn't matter whether it's AC or DC, as long as they're compatible, so which means AC powers the AC device, DC powers the DC device. But then we started to have centralized electricity generation. We generate a lot of power, then we distribute them for long distance. And when you distribute them for a long distance, if the voltage is low, the current will be high. And the loss will be I squared R, right? So you create a lot of losses on the line. So you want a high voltage to transmit so that you have low current, so therefore the losses during the transmission will be limited. But the problem with DC is you, at least at that time, there's no way to convert that high voltage DC down to a low voltage DC. Now we can do it, but at that time you cannot do it. Of course, on the generation side, you can design a generator that generates like 110 volts DC or 110 volts AC, but you can also design a generator that can produce a 13,000 volts DC. Okay, that's okay. So you can design a generator DC which generates a very high voltage and you can transmit. But once it gets to a point people want to use it, at that time, the only way to drive another generator, like a DC motor, and the motor will generate a DC, drive a generator. So the motor is high voltage input, but the DC generator is a low voltage DC output so that you can use it. Apparently, it's very uneconomical, right? So and then Tesla found that actually we should use AC. And AC, you can generate a voltage, certain voltage, and you increase the voltage using a transformer. I think in 210 you guys probably learned a little about transformer. You can have a very high voltage transmission, and down to the user side, you step it down to a low voltage AC. And if you need DC, you'll rectify it. Okay, you get your DC. So this is very simple. Now the voltage transmission, depending on where you look at, it can have all kinds of voltage levels. Like in our homes, we all have 110 and 220. And in our universities, we also have 280 three-phase. We also have 480 volts three-phase. That's like inside the buildings. And between our university or between your subdivision and what we call the substation, right? So the substation takes a high voltage DC, converts to 480. Okay? And between substation and a central station, it usually goes to either like 10K or 20K, depending on the distance. For really long distance transmission, you can see 300,000 volts or even 50,000 volts AC. Okay, so that's history. But with semiconductor devices, today, we are already talking about DC transmission. So the reason that we can use power electronics to convert AC into DC and convert DC into AC, regardless of the voltage, regardless of the current. And it can be made more compact, it can be made much smaller. So today, actually, people are already doing one thing called solid state transformer. So we no longer use a iron core transformer, we use a power electronics transformer. We can transfer 10 volts, 13,000 volts DC into, say, 400 or 800 volts DC. Now think about your battery charging for EVs, right? That's DC, 600 volts DC. Think about solar panels. Right? They generate actually DC, 1.2 volts DC each cell, and you put all cells together in series, you get a DC. So now we have to convert that 1.2 volts DC into 110 volts AC so that it can connect to our home system, right? So now, of course, that's kind of high power, but in low power, we also need some sort of sometimes DC, sometimes AC. So the actual rectifiers look like this. You have 120 volts coming in, of course, can be any voltage coming in, can be high voltage depending on what type of application. For signal applications, you can always look at low voltage. In Asia, Europe, it's 220 volts, here it's 110 volts. Through a transformer, so that's high voltage become a lower voltage. With a lower voltage, like 5 volts or 10 volts, you rectify them. You rectify them, so initially it's like AC. Okay, it's high voltage AC, low voltage AC. And when you rectify, it becomes like sort of half wave. And then you would do the filtering, so the waveform becomes better, look like DC. And then you still have ripple, but then you use a voltage regulator. It can be linear or nonlinear, and it got a constant DC output. Nowadays, you can buy a little like 3.3 volts power supply online. It can give you a precision of 0.1% precision. So which means you can precise to 2.999 or 3.001. So that's kind of precision you can get with a voltage regulator, which you can get. What that does is that it gives you very accurate reading of any input. So very slight change in terms of input, you can use your microcontroller to read it very precisely, very accurate. So a simplest rectifier is just a single diode. All right, you get a single diode, you connect to your load resistance. So your input is AC. The black curve here is AC. And when the voltage is positive, your diode would conduct forward. When voltage is negative, your diode is reverse biased, no current. So you guys already know, familiar with this. So you get half wave. If it's ideal diode, and then the black curve, would just overlap. But if it's a non-ideal diode, there's a 0.7 volts drop on that diode, okay? That's kind of rectifier. You might say, okay, this is changing waveform. Do we have to consider the small signal? Yes and no. Yes means that it does impact like the regions when the voltage is low, but it doesn't really impact the overall, like the peaks when the voltage is above a certain level. Also, it doesn't impact when the current is quite big. Remember from the previous example, the current was like 5.6 ohms in comparison to 1,000 ohms. It doesn't really change much, right? So, but that 0.7 volt drop is real. So we have to take that 0.7 volts off the total. So that's the blue curve that you get is the output, okay? So that's what you get. But if you do this directly from 110 volts, you have a couple of problems to the power supply. First of all, the diode has to be a high voltage diode. It has to be able to withhold like 110 times square root of 2. Remember, 110 is the RMS, root mean square volume. The peak is 110 times square root of 2. So that's more like 150, 160 volts. And plus our input voltage one time changes between like 90 and 120. So your diode has to be able to withhold the highest voltage possible, right? So that's one problem. A second problem is that after rectification, you got this 155 volts minus 0.7. So that's very high voltage. For most of our laboratory like applications or low voltage applications, you cannot direct use it because the voltage is too high. If you want to get from 160 volts DC into like a 5 volts DC, ideally you can use the Zener diode. But the problem is that the Zener diode is 5 volts and input is 165 volts. You drop 160 volts on the Zener is going to have a lot of power consumption, right? It's very hard, it doesn't work. Okay, so what are you going to do? Well, we use transformer. So this texting, guys, learned something into 10, a little bit, I guess. Do you have a transformer come in and gives you 110 volts? You have many tens. And on the secondary, you have not many tens. So the voltage ratio between input and output is a number of tens. And so if your input is let's say your input is 110 tens, your output 5 tens. So now your input is 110 volts, your output will be 5 volts exact. Okay, of course, the real tens can be different, can be 1,000 or 5, depending on the current. The more current, the less tens, the less current, the more tens. But the ratio can be designed. So once you have a smaller ratio, and then your output will be, voltage will be smaller. So in this example, it got the transformer with a certain tap. What the certain tap does is that it reduces the ratio of tens. Like in the pre-example, I said 110 to 5, right? The ratio is too high. So say, okay, can we do 110 to 10? Yes, you can, but the output will be 10 volts. How do you get 10 volts to 5 volts? Well, we use a certain tap. So because of output is 10 volts, each half will be 5 volts, right? Again, the 5 volts is AC. So we use that AC to rectify the top one to get this, the black curve, and we use the bottom one to get the dotted curve, to get this one. We add these two, we get actually a pretty good full wave. So I think the explanation is that when the voltage Vs is positive, current goes this way. When the voltage is negative, it goes this way. So all current goes to the certain tap. So that's how current flows. When it's positive, the top half D1 conducts, the current goes through resistors, and it goes back to the certain tap, form a loop. When voltage is negative, the bottom diode conducts, and the current goes through diode 2 and goes through load resistors and come back to the certain tap. So you get a full wave rectifier, yeah.
Other side, it either is moving one way or moving a different way.
That's right, yeah.
And then the diodes are kind of like gates letting out each.
Yeah, it's only let the positive current flow in that direction. So it's only conduct half of the time. D1 half and D2 half, negative half, positive half, D1, negative half, D2. Yeah, go ahead.
Positive plus the negative.
It's only half of the voltage, you see. Yeah, because when D1 conduct, only the top half work, right? When D2 conduct, only the bottom half work. So it's a half wave for each half of the transformer. So that's the waveform you get. And then we can do some analysis later in terms of, so instead of, so you guys are pretty smart looking at the previous example, you only get half of the time the transformer works, right? So the other half you basically lost. So from the input perspective, like I give you like a full wave, you only use half of wave. Even though we have two portions work together to make it a full wave, but we actually lost half of the waves. So how do you get a full wave? You don't lose anything. That's why we use this full bridge rectifier. The full bridge rectifier works with like 4 diodes. And apparently the 4 diodes together, it will prevent current flow in certain directions. It will let current flow in certain directions. So on the top, the graph is the original graph. And you can see when Vs is positive, what happens? Yeah, when Vs is positive, when Vs is positive, you can see that D1 and D2 conduct. We just simply call it conduct. They can call forward biased or whatever. The reason is, if we draw the curve, you can see when it's positive, D4 is going to be blocking. So D4 is off. And it goes through D1, and D3 will not let it go. So D3 will not let it go. So it will only let it go through R. And once it hits here, it will go through D2 and will go back. So that forms a loop. Right? So that's where you see here. That ground at D2, forget about it. I mean, it really doesn't do anything here. But of course, it tells you that there's a ground for the DC voltage. But in fact, it goes through D1, and then no, actually, this drawing was It goes through D1 and then R. Yeah. That's how it goes. But when DS is negative, and you can see when D1 is negative, it will come this way. So D2 will prevent it to flow. It will go through D3 and then through the resistance and then through D4 and goes back. So it's D3 and D4 is on and D1 and D2 is off. Now in each direction, of course, you would have 2 voltage drops. So it's 1.4 volts drop. So the voltage drop is 1.4 volts in each direction. So now you can see, regardless positive or negative input, you really have the voltage utilized. So when the positive, it goes this way, when negative, it goes this way. And the R over here accepts positive half and negative half, except the 1.4 volt drop on the 2 diodes. And one time I think a student asked, why is 1.4? Why is it not 2.8? You got 4 diodes.
You're only having diodes in your set of.
Because at each time, only 2 diodes are conducting. The other 2 diodes actually are blocking. So you're not flowing currents through all 4 diodes, right? So at any given time, you only have 2 diodes dropping 1.4 volts together. So this is very simple. But at this point, you might say, okay, well, nice waveform. There's a blue waveform is what we get. Nice utilization of the transformer, and everything seems to be great. But the problem, of course, is that even though the blue waveform is kind of always positive, but it's not a constant. It's like a pulse come in. So what can we do with it? Well, capacitors, right? You guys know filters. So that waveform means it got some, because if you look at waveform, you do integration and you do this, you find that there's average of that waveform, or RMS, whatever you call it. And that average is somewhere over here. And on top of that average is some AC. If you get a low pass filter, I mean really low pass filter, you have to filter out that 50 hertz, 60 hertz. The DC will be able to pass, but then the AC is filtered on that thing, right? So you have to have a filter. So that filter works to get your DC output. So that's what we're going to look at as the next step. We'll put a capacitor. In this example, there's no load connected yet. So if you have a capacitor, think what happens when the voltage is positive. The diode is going to conduct, it's going to charge the capacitor. How much voltage, how high is the voltage going to go on the capacitor? It's going to go whatever the Vs peak is, right? So it's going to, whenever the voltage goes up, the voltage on the capacitor is going to go up until it reaches like maximum. And then when the voltage Vi drops, what happens? When Vi drops, VO is going to be more than Vi. So VO is more than Vi, which means D is blocking, reverse biased. So therefore, no current, right? So when Vi larger than VO, so there's ID increase, will increase until that our VO equal to I max. And then once it's charged, VO is going to be larger than Vi. When Vi drops,
Where does the current go?
the current goes to the capacitor. When it's dropping, when VO is larger than Vi, D is off, no current. Current cannot flow, right? So ID is
That means
0. So VO is going to be constant. It's not going to change. It's going to stay. The voltage on the capacitor is not going to change. It's going to stay, okay? Because there's no current pass, right? So it's not going to flow. So If you look at the waveform, on the very first waveform, the capacitor is charged all the way to its peak, and it's going to stay, regardless of what changes later, because no current can flow back. And would it charge again next time? Like, would it increase more? No, because when the voltage is less than Vp is less than Vo, it's not going to increase with the voltage on the capacitor because no current can flow. Okay, so this is the idea. Like, okay, we got a really perfect DC waveform, but the problem is that as soon as you add a load resisting parallel with C, that waveform is no longer going to hold, because what happens?
When the voltage isn't providing for the capacitor.
Yeah, as long as you add a resistance on in parallel with the capacitor, so yes, in the first cycle, it's going to charge the capacitor, it's going to have current flowing through the resistor, and the voltage on the C is going to increase. But as long as we add less than output, what happens? The capacitor is going to supply current to the load. No current flowing back, no current flowing back. But there's current going to flow from C to R, from C to R. When current flows from C to R, what happens to the voltage across C? It's going to drop. So that's where you see the waveform. That's where you see the waveform here. See, it's going to charge to the peak. It's going to drop. And at the next opportunity, it's going to charge again. It's going to drop. It's going to charge. So that's how it looks like on the top. That's how the output voltage looks like. Every peak is going to drop. Now, depending on how big is the resistance, right? If the resistance has a very high value, the drop is small. If the resistance has a very small value, like 5 ohms, for example, and the voltage will drop very quickly. So actually, you could have waveforms like this, but I can draw a couple of different waveforms that you guys can look at. So it could charge like this. It could drop like this. Okay, but if the resistance is too small, you can actually have drop over here. Yeah, I have to figure out how to change the color. I will call them next time. Okay. But if the capacitor, if the resistance is too small, and the current could drop like too much, voltage could drop too much, drop to this point, or it could drop actually to 0 before the next cycle comes. So in this case, what can you do? You know, to increase the to reduce the ripple.
We could use that transformer.
Right. Yeah. No. Well, what you can do is, well, one thing, of course, you don't use that large, small resistance. You use a large resistance, right? Of course. But if your resistance is given and a small ohm resistance, you can increase capacitor. Because what does this correspond? Change. It's RC. Okay. If RC is very big, you know, and then your reduction will be slower. So increase C will reduce the ripple. Now, the other thing that you're right too, because if we do this half wave, it takes a long time, right? So between half cycle and other half cycle, this in the middle, there's nothing, right? So if you do actually the full wave, that will reduce the capacitor by half, because you only wait for half of the time, your capacitor will be charged again instead of like a whole cycle. This is how, if you have a full wave, yeah, and then you've got a much better waveform. But if you don't have a full waveform, you see what happens? It will drop all the way to here, and it will increase, right? With a full wave, you reduce the ripple by half. Now also, I think we're going to stop here. So we're going to get super dies next week. And also, next week, I'm going to do some equations on how to calculate those like time and C and so on. So, and also maybe if I have more time, I will do more examples to have you review a little bit on op amps. So have you guys prepare for the final exam. Oh, no, middle, the first middle term. Yeah.
What